Hi! In the fourth and final part of this tutorial on BERT classifier fine-tuning, we'll discuss training with Catalyst, and I will also spend some time showing how to use GPUs. That's an extensive topic, but I will just show how I typically run models with GPUs, and we can also discuss having an instance on AWS instance running, and we'll see how it actually looks like running a model with GPUs. How it's different from using just Kaggle notebooks and or Google Colab. So the whole idea of creating this small library is to provide a more disciplined way to train models. So not just running a notebook from start to end, but having a nicer modular approach, and we'll see how it actually works. So just running training on a GPU and then monitoring logs. I will just share my experience with that. Okay, so far we covered an introductory part, and then we dived into all the data preparation for the model, and then we discussed how the model itself works, and now finally training. So yeah, that's why all the logic of the source code of this small library. So data, model, and then we dig into training. Let's look at the code, and then we'll use a Jupyter notebook to run it and to understand it better. So we import this method read data from our data. So it's all about data preparation. And then from our model, from the file model.py, we import the model, BERT for sequence classification. And we probably have some utils. We load hyperparameters with some utility function. So it's our YAML file, config.yaml. Then we create loaders. So it goes from this method read data. And I think I need to zoom in a bit. Oh, right. Then we define the model. And further goes, PyTorch, so defining criterions, optimizers, and then further goes Catalyst. So let's cover this part in detail. So I'm going to copy all this code into Jupyter notebook and then go step by step. Right, so therefore I'll start with imports. We'll load some specific Catalyst objects that we're going to discuss, and we'll also need just torch. Okay, let's start with that. Okay, the simplest thing to start with is just to import something. Okay, we'll need torch and then some specific Catalyst objects. Yeah, and I think at this point it's good to print versions of the libraries that I use. Let's just print torch version that I'm using here, and then same for Catalyst and HuggingFace. 151 for torch. Let's also have transformers imported. Okay, let's just import transformers. Well, I'm not sure whether in future they introduce some non-backward compatible changes, so that's okay. It's a good idea. Let me check. Did I provide requirements file? Yeah, I think I did. Okay, requirements. Yeah, we can see versions here, but I will have the same in Jupyter notebook. Transformers 351, and finally let's just do the same for Catalyst. Okay, and we need to import just Catalyst for that. Import Catalyst. Okay, it's not the latest version, but anyway, so far the versions are backward compatible, so that would work. Okay, so what we actually need to train a model with Catalyst? So we need to provide basic ingredients for training, and so these basic ingredients would be our criterion that we are optimizing, then the optimizer itself, and optionally a scheduler for the optimizer. So let's copy this part and briefly discuss it. Right, so we're solving a multi-class classification task, and yeah, classic loss function for that is cross-entropy loss. So it works really well, and it's a theoretically well justified loss function in this case. We'll be using classic Adam optimizer. The only thing that for transformers you typically need a lower learning rate than for computer vision tasks. So something around 10 to minus 5 works well. I'll just specify the same as I did in configs, 3 times 10 to minus 5. So transformers need much lower, so 2 orders of magnitude lower learning rate than a typical computer vision task, so a typical computer vision model. And then we'll turn on scheduler, so reduce on plateau, so it means that when the loss is more or less constant, then learning rate will drop. Okay, so these are basic ingredients to solve a multi-class classification task. And then further, we will define a runner, and we'll run runner.train, and then to run predictions, we'll do runner.infer. So let's see how this works. I'll copy setting seeds for reproducibility. And my favorite seed is 17, but this can be any number. And this prepare QDNN function it's a utility from Catalyst. Yeah, so Catalyst utils prepare QDNN and then set global seed. So basically it just fix all seeds for NumPy, for Torch, for QDNN, so that results are reproducible. To be honest, they're not fully reproducible for me in a notebook, but I checked in code, it works. So if you run Python src/train.py multiple times, it would produce the same results with fixed seeds. Okay, so now let's copy the definition of our runner and then runner.train. Let's take a look at this supervised runner object. It says it needs, so that's some utility, some object which is going to perform our training. And we see that it needs a model, a device. So this either we train with CPUs or with GPUs. So we'll specify the device here. And we see that it expects some input and produces some output. So by default, input key is features. So it expects a data loader to prepare dictionaries which have a key features. And the output key by default is called logits. So it produces some scores called logits. We also have an attention mask, so that's why we'll create a runner and we'll change an input key saying that we have both features and attention mask. And now finally how the training itself looks. So we'll pass the model, the criterion, optimizer, scheduler. Then we also have train and validation loaders. Remember it's a dictionary with keys train and valid. And so these are 2 PyTorch data loaders. And then we'll also pass 2 callbacks, so accuracy callback to track accuracy. And here we also use optimizer callback to turn on gradient accumulation. Probably I'll need to leave some link here explaining gradient accumulation. Well, not explaining, but just a post describing gradient accumulation. But basically it's we are doing optimization steps, so actually changing model weights only once for 4 backward passes. So we accumulate gradients for 4 forward and backward passes, and then only once in 4 backward steps we do the actual model weight updates, so the actual optimizer step. Then we also specify the log directory, so here we'll have a lot of information including checkpoints and logs, and so just in case I'll empty it first. Right, and then we, for a small example, let's just train for one epoch. Right, and we set reproducibility, set all these seeds here. So let's redefine our training and validation loaders. So let's go back to data preparation. Because we are doing one additional step in for the training set, we shuffle data, and of course it also depends on the random seed. So let's copy this definition, and we'll also need a test data set. So let's just copy it all here, below the setting of all the seeds. Right, and we'll have a test loader as well. So I'll create a similar thing, but for the test loader to run inference. Okay, actually we can have multiple loaders, but we'll have only one. Test loader, it will use a test dataset, and we need to define. So let's just redefine all datasets again to have everything in one place. Okay, we need to copy these two, and we'll have a test dataset as well. Okay. And also let's put a more realistic max sequence length, not 16, but something closer. Let's take 256 for an example. Yeah, let's have it as a hyperparameter, max sequence length 256. Well, 512 will work better. Okay, it's with such a small example, it's not a big deal. Let's fix it for 512. And then we pass it here and here, and we also have a test dataset. Right, so here it only changed to test data frame, but for a test dataset we do not provide labels, so we just don't have them. Well, we do, but we don't use it here. Right. So then let's just redefine loaders. Okay, and now we have everything for training. So yeah, let's run training. Okay, so sometimes probably we need to fix. Okay, forward got an unexpected argument features. Okay. Yeah, it should work. So we define runner. So we specified that we pass features and an attention mask. Okay. Yeah, that's strange. So it used to work. Forward got an unexpected argument features. Okay. We didn't check. Sorry, yeah, I think I skipped one part with our model. So we understood how the model works, but we didn't actually try it against some realistic mini batch. And this is a very important step. So, yeah. Okay, sorry for jumping back and forth, but once we defined our model, it's really important to run a mini batch through the model to see that it works. Otherwise, if we launch training with Catalyst or with pure PyTorch, we might be lost. So it's actually a good example here. Yeah, so it used to work for me, but now, okay, I experienced maybe some problems. So let's just make sure that our model works. Okay, now I understand the issue actually, because we are passing the model, and that was a distill BERT model. It's not the model that we defined. It's not BERT for sequence classification. Okay, so I'll go on here. So our model is indeed not what we need. It's a distill BERT model, while our model that we'll use for classification is a bit more involved. So that's why this problem. Okay, so we need to define this BERT for sequence classification model, and let's also run a mini batch for this model to make sure that it works. Right. Okay, so we'll create a, let's call it CLF model, so model for classification. This will be our BERT for sequence classification model. Autocomplete, does it work? Okay, BERT for sequence classification. I'll just run it again. Okay. And we need to pass the pre-trained model name, which is our distilled BERT based on cased, saved here as model name, and the number of classes is 5. Okay, so we also initially had some mini batch of data, just a very small example. And let's run this example through our model to make sure that it actually works. Yeah, it should have been in the third part, but it's yeah, where we discussed the model, and it's really very, very important. Okay, it says that attention mask is none. So we passed a dictionary, but let's actually see what we need for the forward method. Okay, remember we defined it that we needed features, attention masks, and head masks, and we passed a dictionary. That's not a good thing to do. So we can actually extract all the keys from this dictionary, right? So we here in this mini batch, so it's a dictionary, and we have exactly the same keys as we need, right? And so we can use 2 stars to basically provide features as a separate key, attention mask and the head mask. Well, we will also pass targets. Maybe we wouldn't like to do that. Okay, it doesn't like targets. Okay, let's do it in a clean way. So we pass features, right? So this forward method needs features, and then it needs an attention mask. So let's pass it explicitly. So as features, we'll pass mini batch and the key features. And as an attention mask, we'll pass the same. So from mini batch, we are taking attention mask. Whew, okay, it works. So we can pass a mini batch through for our model, and in the end, we get what we need: a batch with sizes 2 by 5. So batch size by the number of classes. Okay, good, it works. So now we need to pass this CLF model to Catalyst. Okay, and now it should work. Okay, so we see training starts. Yeah, so TQDM prints some logs. Okay, we have only 150 examples and batch size is 2, so that's why 75 steps, and it's only 1 epoch. Okay, let's wait a bit here. Yeah, the TQDM doesn't work ideally at the second time, so ideally it needs to draw a nice bar and update it. And now it prints it all at a new line, so each new iteration is a new line. Okay, it's not a problem. Just a bit later we'll run training with GPUs, and I will show a more disciplined and nicer way to track logs. Well, actually eyeballing it with TQDM is also fine, so we can see, yeah, we can take a look at the log, sorry, at the loss, and see that it fluctuates a bit, but in general it decreases. That's a good sign, but of course it's not perfect way to monitor a model training. Okay, meanwhile we'll copy the implementation of the inference step. Well, so just in case, probably we empty cache in CUDA to save some GPU memory, but right now when we train with CPUs we don't need that. And so then we'll run an inference step, and then we'll produce predictions. Right, so I'll just split here. Okay, so for the inference step, so once the model is trained, we'll provide the same classification model for the inference step. We'll pass our taste loader here, and then we'll use a couple more callbacks. So the checkpoint callback will be able to pick up the best checkpoint, and we need to provide path to this checkpoint. We'll see now how it looks, what is saved there to the log directory. But basically we'll have checkpoints there, and we can pick up the best checkpoint, so best in terms of validation loss. That's a really good feature, so that we can automatically pick up the best checkpoint, and not so just in case we overfit it, we can still pick up not the latest checkpoint, but the best one. And then the inference, this infer callback, will be used to actually get predictions. Right, and then after that we will take the predicted scores, and this is not trivial, yeah, so not intuitive, so that we need the runner and then callbacks number 0, and then we take predictions and then finally logits. So that's a bit annoying. And then we will save predictions to some path. Data, I have output. Yeah, this can be anything. So pret.txt. Okay, our training goes on. One epoch is done, so further we go with the validation set. And this is also done. Okay, and so it says that it saved a checkpoint. We run it only for one epoch, so that's why it's also the best checkpoint. And we can see the final loss. Okay, that took quite a while with CPU. So of course nobody trains models with CPUs, so we'll run the same much faster with GPUs. Okay, and now we have yeah, the log directory. Sorry, it's here. Yeah, so we have a log.txt file, so exactly the same what's output here. Yeah, we can have it in a txt file, and it also saves some TensorBoard logs, so for training and for validation. We'll take a look at these later. And we also have checkpoints. Yeah, so we see if we analyze the size of this directory. Yeah, it's 1.5 gigabyte, meaning that it's, well, most of this space is occupied, of course, by checkpoints. And we see that it saves a lot of checkpoints. So the best checkpoint. So for DigitalBERT, they're pretty small, they're just around 250 megabytes. And for a larger model, that would occupy more space. But it saves checkpoints for each epoch. It also saves last checkpoints and the best one as well. I don't remember this difference between best and best underscore full. We can check it within Catalyst documentation. Okay, so it saves all the necessary checkpoints, and then further with the infer method we can automatically load this checkpoint, and then we run inference against the test set. Yeah, with the 512 tokens as a max sequence length, yeah, with CPU it takes, you see, it's really slow. So just for 150 examples it takes almost a minute. Okay, but here we'll wait a bit while it's done. What I found a bit annoying is that if you'd like to run this against a small mini batch, then yeah, by default it saves a lot of checkpoints, and yeah, you can actually play around with that. So if you add checkpoint callback here as well, there is a flag save and best. If I remember correctly, it's this. You can add a checkpoint callback here. And then it will have a flag save and best, and you can set it to 0, so it will yeah, I'm not going to check this, so I'm just that's just how I remember it. I'll double check later, but basically it just saves now only the last checkpoint and the best checkpoint, and it does not save intermediate checkpoints at several epochs. If you specify 4 here, it will save 4 latest checkpoints. No, sorry, 4 best checkpoints. But now with this flag, it saves only the last and the best one. Right, so the inference is done, and so finally we have predicted scores, which we can save to a file. And predicted scores are, yeah, it's just an array. So it's, yeah, you see it's 5 by, so it's, sorry, 1. It's okay. It's a NumPy matrix, so it will have shape. Yeah, 150 by 5. Okay, so the final step would be evaluating predictions. So yeah, this part is probably, yeah, there's some boilerplate code, but I actually would like to calculate F1 score and by class as well. So we can load predictions from this file that we just created. We only need this mapping from the predicted indices to the actual classes. So remember, in our training set, we had, so the training dataset learned this label dictionary. So we can create an inverted one, so to map this, 1 back to 7 and to map 2 back to 8. Yeah, we can simply take all the labels from the training set. So if we just take unique, this will be 1, 7, 8, so the keys of this dictionary. So these are two alternative options. So let's just take presented labels, and then we load our scores, so this matrix, and then we need to go through each row, take an argmax, and then look it up in these present labels. Yeah, so present labels will be just 1, 7, 8, 12, 13. So we go through predicted scores. Let's just print several rows. Sorry, that was semicolon. Okay, so we go through a row, we take an argmax, so in this case it's, yeah, this one. Argmax will be 2, and so then we further take a look at this list and pick up the element with index 2 will be 8. Right, so F1 scores, yeah, are pretty low. Yeah, but these are only 150 examples. Well, still they're too low, actually. With a smaller max sequence length, I had better results. Okay, so something at least around 0.5 or 0.4. Okay, we can play around with it later. And it's also interesting to take a look at micro F1 score and macro F1 score. So macro would be, so we first will be averaging across classes, and micro will be actually same as accuracy. And a small classification report with some small utility function can highlight, yeah, this. We can report F1 scores, in this case precision, recall, and F1 score by class. And yeah, if we'd like to, we can highlight some of the rows where metrics are higher than some threshold. Well, to show how it works, let's put 0.3 here. But yeah, the results are not really good with this small test data set. Okay. Now I would like to show you how it looks with GPUs. It's not a good idea actually to use Kaggle kernels or Google Colab all the time. So speaking about GPU instances, yeah, if you go to your AWS console and if you just search for deep learning, so there are some dedicated instances for deep learning. So it's well described here. What is the AWS Deep Learning AMI, so Amazon image? Yeah, so it's called DL AMI, Deep Learning Amazon, what is it, machine instance. And this guide, yeah, describes how to launch it, how to get started, what are the instance types, yeah, how to launch an image. So it's well described on Amazon, and you have a lot of blog posts for that. Let's here only describe the choice, so how to select an instance. Okay, so we need an instance with a GPU. Well, it recommends some GPU instances Well, these are pretty expensive ones. So yeah, they have some 4, 8, or 16 cards on board. Yeah, Amazon is doing a good job. Yeah, recommending pretty expensive instances. Well, and a more advanced scenario would be to use distributed training, and Catalyst supports these out of the box. So a good idea would be to shoot an advanced tutorial on distributed training. So for some large tasks, it definitely makes sense to run the model on several GPUs in a distributing mode. Okay, so something more realistic, yeah, we can take a look at at spot instances and take a look at pricing. So P2 X large, this is a more realistic instance. Well, I wouldn't say realistic, but it has only one GPU on board, and it costs just 27 cents per hour. With Linux and Windows is almost twice as expensive. And so this has we can check. I guess it has V100 on board. Okay, we can check specifications, but this is only one GPU. Okay, let's check it here. Amazon P2 instances. Okay, P2 X large has one GPU, 4 CPUs, 60 gigs of RAM. If you run it on demand, you see it's expensive, and as a spot instance, it's much cheaper. Right. Okay. It doesn't show which GPU that is, but it's okay. It's okay. It shows it here. That will be a K80 GPU. Okay. It's a modest one, not the latest one, but yeah, serves well the purpose, at least for training small models. Right. Okay. So then, if you just follow this tutorial, you can launch an instance, and then you'll have some IP address to SSH into. Right. And now, okay. Sorry. Just I need some 30 seconds to share my console with you. Okay, I would like to show my terminal and how I actually launched training with Catalyst on a dedicated machine. Right. Okay, there it goes. Okay, once you've launched the machine, you'll have some IP address, so something like maybe this, or maybe a bit different. So you can SSH into your machine, and I will just barely clone our repository. So the repository that I shared, BERT fine-tuning Catalyst. I will just clone it from scratch. Okay, I have it here, but let me even delete it and freshly clone it. Right, okay, so now we see all the files. Let's go to this directory, and we see all of the files here as well. Okay, and so if we just follow the README, we can simply run Python src/train.py. But first of all, let's check that we have a GPU on board and that it's gonna work. I'll just customize it a bit. Okay. Right. Okay. So so you launched an instance, and just to make sure that it has GPUs on board, so the first command to run is NVIDIA-SMI, and indeed it shows a K80 GPU on board. So it's something about 11 gigabytes of memory, and now currently it's not occupied. Yeah, it says that it's Tesla K80. So indeed we have a GPU. And the second thing to check is whether it's configured with PyTorch. So I actually have an environment for that. Let's just check with system Python. So you import torch. Okay, so you see it doesn't work with system Python. So it's a recommended way to do that is to have an environment. And so here I have a conda environment. Conda envs list. Conda env list. Okay. Right, and so I have a dedicated environment for that with all the dependencies. Okay, and now I can run Python and check that CUDA works. Import torch. And then torch CUDA is available. So that's essential thing to check. Yeah, that it shows true. Then it means that torch is configured well with CUDA, with QDNN, and if that doesn't work, then you have to run through all these tutorials, and maybe that's actually annoying to set up a driver and then a QDNN version and then CUDA version and make sure that in the end it all works. Now it says that torch is ready to be used with GPUs. Let's just check the version. 1.2.0. Okay, that's not good. I guess it's a dependency. So this deep learning image goes with pre-installed QDNN. So in my case, it's not the latest version. If you run again NVIDIA SMI, yeah, it shows CUDA version as well. Okay, it's not the latest one, and so that's why I had to install not the latest torch version as well. In your case, that would be something closer to 1.5 PyTorch version and CUDA 12 or the latest one. All right. So now we can run, just following README, we can just run Python src.train. And now it trains with the GPU. Now it would run much faster. Okay, it still needs some time to create, to load all the data. So it needs to initialize the model. I think most of the time it was downloading weights of the digital BERT model. So next time it will run much faster. Again, now you see that instead of a minute, yeah, we trained one epoch in 8 seconds and just 1 second for inference. So now it runs much faster. One more step to show. So first of all, let's check configs, what we trained this with. Yeah, so we used 256 as max sequence length. We trained for 1 epoch. Batch size is 16. With GPU, it's really important to configure these two params, batch size and max sequence length. So this depends on your GPU memory on board. So we have 11 gigabytes of video memory. So then, yeah, it takes some effort to configure these two. So the larger the max sequence length, the more memory you need, and same for the batch size. So yeah, if we specify a too large batch size here, that wouldn't work. It would say that GPU ran out of memory. Yeah, if we set something unrealistic here, that wouldn't work. Just in case, let's remove logs and run it again. Okay, so final thing that I'm gonna do is overfitting this model to a small mini batch. So that's one step that we skipped, but it's really important. okay, indeed you see that it's ran out of memory, so you have to configure it carefully. So this combination of max sequence length and batch size, okay, so 16 works, and while it's training, we can actually take a look at how much memory it uses. Yeah, I really missed some handy calculator for GPU memory, so how to tweak these parameters and not to run out of memory. All right, so one important step. Okay, I see that my image is no longer seen. Okay, I'll show myself again. Okay, here I am. Right. So one important thing is once you've defined a model, and once you've made sure that you can run a mini batch for your model, it's really important to make sure that you can overfit to this small batch. So just run your model for some 20 or 30 epochs and make sure that it is able to overfit, that the model has enough capacity to overfit to this mini batch. So let's do just that. Now I'll train the model for not for one epoch, but for 20. Or even let's put 25 for 25 epochs. Well, with these toy files, it's yeah, this is not going to take too much time. And then at the same time, I'll show you how to monitor logs and how to run training in a way that we can resume it at any time, that it does not fail, and how I typically do that. Right, so instead of just running the command like this, so instead of just this, what I typically do, I create a daemon process for that, so that we can launch it and yeah, forget about it, and we can actually log out from the machine. And I typically forward all the output to some local log file. Well, with Catalyst it's not needed because well, Catalyst takes care of all the logs by itself. But typically if I run just some long process, I run all the output to a file, and then I remember some incantation. This thing means that whatever it produces, it still forwards it to this log.txt. This ampersand 1 means the argument, bash argument number 1. So the 0th is probably this one. So the number 1 will be log.txt, and it outputs all the everything printed to this log file. Okay, and so now we launched training for 30 epochs. So we can take a look at this log file, log.txt, and the flag -f means that it shows the end of this file. So it's being updated, and will be showing only yeah, what's added to this file. Okay, now we see that we launched training for 25 epochs. And one good thing about Catalyst is that it also it also writes all the logs to the same directory. So here in log.dir we have checkpoints. Yeah, we've got the same log.txt file, but we also have these training logs, and we can pretty simply use TensorBoard with these logs. So TensorBoard is a small utility, and it's pretty popular, pretty simple, and yeah, even PyTorch fans still use TensorBoard to monitor training. Okay, so we can run TensorBoard and then provide log directory, and in our case it's called the same, and I will just change the port. So by default this port is 6006, but I will specify 8888. Yeah, just because this port is open to the outer world on this machine, but you can specify this in AWS setups. It's actually, well, 8888 might be needed for Jupyter notebooks. Okay, 1, 2, 3, 4, I think it would also work. And One final flag that you have just to memorize: bind all would make it work from a remote machine, so that you don't need to do port tunneling. Okay, it needs to print something. Okay, it takes some time. And then you can go to your machine. So in my case, it's this one, and then port 1, 2, 3, 4. Okay, I'm still showing. Yeah, I have to switch to browser. Okay, sorry, for me 1, 2, 3, 4 doesn't work. Okay, then I'll check 8888. Okay, right. So yeah, I'll switch to the browser now. Okay, now we see training logs. So yeah, Catalyst writes training and validation logs to this directory, and TensorBoard picks it up, and now it can plot. So here in blue it's training accuracy per batch. In red it's validation accuracy per batch. Same for epoch. So we see accuracy is increasing, and then the loss function needs to decrease. Yeah. So. And the same, the loss function per batch and then per epoch. And so far we've covered 5 epochs. And we'd like to make sure that we are able to overfit, meaning that the blue curve needs to fall to 0, almost 0. And then probably at some point, yeah, we'll be overfitting. So the red curve will be dropping, then it will, at some point, it will change sign. The loss will start increasing. And it's a very good thing to check that we can actually overfit to a small batch. Okay, so we'll get back to these logs. Yeah, now I need, probably a second tab. Yeah, I'm not using TMUX. Okay, I'll stop TensorBoard for now. We'll get back to this a bit later. Okay, so we basically need to wait a bit for some more time here. We see this time with GPUs, yeah, it runs much faster, so it's not a lot of time to wait till it fine-tunes to 25 epochs. Right, yeah, we see that one epoch takes some 40 seconds. Okay, but I'm not gonna wait till that. I will show a nice picture once the training is done. So you'll find it in the same notebook. But this model works well and it's able to overfit, so we'll see classical overfitting curves. So the training loss falls to 0, and validation loss starts increasing at some point. And remember, once you've defined your model, it's essential, it's very important to run a mini batch through this model to make sure that it works. Otherwise, you'll be you'll be lost in debugging this model, and then checking that it's able to overfit a small mini batch. That's also essential. Okay, that's good. I'll go back to the README. So now you see that, you can actually reuse this small library. So you can just run it as is. So just specifying paths to all your files here in config YAML file. But yeah, once you've covered this tutorial, I think you can now easily customize your code for data processing. You can customize your model. So define a different model, like maybe a scientific BERT by NLP. So you can just import it from HuggingFace, or you can modify the code itself in srcmodel.py. And probably now you can also understand this part, the training file, and now you better understand what's happening, how Catalyst runs training. So one final remark is that, well, for such things where the pipeline is as simple as that, where you just run, you specify a runner, Catalyst runner, and then you have .train, .infer. When it's as simple as that, it's easy to use, and I use it by myself as well. Once things get more complicated, probably you would switch to just pure PyTorch. If you need to do something really involved and there is a risk to have some internal bugs, then it gets much harder to debug. So you'll have to go into Catalyst source code. It's not fun. And well, actually the same for other libraries like PyTorch Ignite or PyTorch Lightning. So if you start doing really complicated things, then you probably would just create this big training loop so that it's easier to debug. Or you just create a small wrapper, so your customized small library to run experiments. Okay, cool. So hopefully that was useful, and then you can now run your models faster with Catalyst. Finally, don't hesitate to read documentations and source code for transformers, and same for Catalyst. So Catalyst goes, of course, with documentation, and it's pretty straightforward. So we can analyze, this Catalyst 101. So meaning these minimal examples, which are very comprehensible. Okay, good luck.